Good morning. It's a new day in the physics shop here, and we are looking at developing a formula for centripetal acceleration. So showing, not instead of just giving you an equation, we're going to show you, and I'm going to show you like why it makes sense. Um, it's a nice little development. Involves some a little bit of calculus analysis and some approximations as what something would be at an instant rather than over an average period of time. So you'll see some calculus kind of work in action here if you've seen that course before, and if not, well, you'll just sort of follow along as well. You don't have to know the actual calculus process, so just the concept that calculus helps us with. And then we're going to work with that equation. So here we go. So you've seen something like this already, where we have a uniform circular motion. We've got velocities at instants, velocity at instant 1 or velocity at instant 2. And so we're looking at a development for the acceleration equation. So of course, it would probably make sense to start with what we know, right? We know acceleration is delta v over delta t, right? If you're trying to work on a development for acceleration and you haven't thought of using delta v over delta t, you should think harder. you gotta start with what you know, of course, right? All right, so delta v, of course, equals v2 minus v1, right? And v2 minus v1 would be a tail-to-tail vector diagram to visualize this stuff, just like we did I showed you in another lesson, of course, right? But we've got that. Oh, this little straggler was. So yeah, we got this tail-to-tail, and you can see like this delta v, towards the center of the circle, like we did last time, right? So we're going to convert this kind of thought that we've already seen into an equation for acceleration with some sort of not assumptions, but I don't know how would you call it. Basically, looking at what happens as you get to a smaller and smaller time interval, as well as the vector subtraction for the velocity vectors. We're also going to look at the vector subtraction of the radius vectors. And you'll see why as we get through the proof development, I guess you'd call it. And so this is the kind of thing I want you to be able to follow along with. But I think at this stage of the game, you wouldn't ever be asked to like do this from scratch. It should be something you can follow along and say, yeah, that makes sense. That makes sense. That makes sense. I might not have thought of doing that, but I mean, it makes sense. All right. So again, I showed, by the way, here both options for vector subtraction. So tail to tail. And if you're looking at the tail to tail version, sometimes people just kind of get messed up as to which way it goes. And of course, this is the initial, because that's your V1. And then this is the V2 over here. So that's your final. And so, of course, the arrow goes from initial to final. With the radius vectors, we're going to look at adding the opposite. And so we have R1 and we have R2. And so we're going to have R1 added to the opposite of, to the opposite of R2, right? So, so we have add the opposite thing. And so you get the same idea. You get, the opposite of R1. Looking at things there. Yeah. Just critique on my own work after the fact here. Negative of the R1 vector. So we have R2 minus R1, R2, R1. Let me just do this on the fly here. So we've got the R2 vector, and we've got the R2 vector, and we've got the R1 vector. Just give myself vectors I can use here. And so we want to do R2 plus the opposite of R1, right? And so I'm going to take that vector. I'm going to basically, oops, here, Control Z. I'm going to group it back together because it ungrouped on me, and I'm just going to flip it around to be the opposite vector, right? And then we get R2 plus opposite of R1, and why am I not getting the right delta R vector? I do wrong here. Yeah. Sometimes when you're trying to check your work or fix a mistake, you just keep looking at what you think it should be, and then you have to switch gears and realize that you should make it what it should be. So this diagram here, I wanted that delta R to be in the same direction as delta V, just because it was drawn like that already when I originally looked at it and thought about it and so on. And, that's just not the case. So problem solved, you got to just look at what it is and make it be what it actually is, right? Rather than what you thought it should be. So the delta R is like that, which you can see I actually already had drawn on the diagram in the original case. All right, so I'm not even going to edit that out. It's part of the process of trying to figure things out if you ever get stumped, right? So there you go. Anyways, there's your radius vector. And so when we look at values of the absolute value, like the size of the velocity, well, we're at uniform speed, right? Uniform circular motion. And so the speed of that is what we're talking about, right? So whether you're talking about V1 or V2, it's the same size all the time. So the absolute values, the magnitudes of them are the same. And of course, the radius vectors are the same as well. They're just going to be the radius. Okay, so if we have an absolute value of R1 or V1 or R2 or whatever, we can just simplify them just being a V and an R, right? And when you look at those triangles, they are both isosceles triangles as a result, right? If you look back at these triangles, you got this one here and you got this one there, and they are isosceles triangles. And they, the V and the R, if you look at the diagram, they are perpendicular to one another. That's just a known thing about geometry of circles, right? That the radius vector is always at 90 degrees to a point of tangency, and so that's just something to know. So that means that the triangles are similar, okay? So by side angle side, in fact, right? So looking at them there, I have this triangle just rotated so it lines up nicer, which is why it was like that on the previous page, right? So I could take the new picture if you want and put it in there as well. I hope, anyways. Let's work on the fly here and paste that in, and you still have the isosceles triangle kind of situation going on, right? And similar triangles because you got side angle side. And so, if you look at ratios of sides of triangles from similar triangle math from grade 11, then we have ratios of sides. And of course, this side is the key one we're going to have to try and work with because we're working towards getting acceleration. Acceleration being delta V over delta T, right? So you can see why I'm going to have these delta R and delta V and so on vectors in there. And why those are just going to become R's and V's, as we talked about before, right up here. So we have that so far. We're going to take that thing, we're going to solve for delta V because we're interested in it, right? And so delta V, of course, just multiply both sides by V, and you get that. And then if we're looking at the acceleration, it's going to be delta V over delta T. So we're going to have that thing over delta T. Okay? So when we look at our average acceleration, we're going to just write it kind of like that, I guess, right? So now this is where, we're looking at a large time interval, right? The thing went through in uniform circular motion all the way from there to there, right? And so in that time period, it's going to travel like a path distance, like a path length of delta S, we're going to call it, okay? So in a large time interval, here we go. In a large time interval, we've got, that being a large value. If you look at a small time interval, then the average acceleration, of course, approaches that instantaneous acceleration, right? Over a super small time interval, you'd be just looking essentially at the acceleration at this spot. And if you did delta V and delta V1 and V2, but super close together, you'd have a smaller time interval, and you'd have an average acceleration that would very much represent the instantaneous acceleration. That's the calculus idea, right? So with our acceleration formula, this is the lingo in calculus, right? Is that you take the limit as delta t goes to 0. That would give us the actual centripetal acceleration. So we're not doing the actual calculus work here. I'm just using the calculus representations of concepts. So if you haven't done calculus yet, it'll be a good lead-in to when you see it. Be like, oh yeah, I'm going to learn the math tricks to do with it now instead of just using the concepts and the ideas of it. But yeah, so we have as the time delta t goes to 0, what you get is this delta r here, right? That vector subtraction result between these radius vectors, that straight line, becomes the same, like it approaches the same value as the path distance, the path length. So yeah, that's their delta S, or path length, right? So now we can say, okay, well, delta S, we can focus on that actual path length, right? Path length is just velocity equals distance over time, right? And so it's going to be distance over time, which is going to be our path length over our time, okay? So if we solved for the path length itself, then we'd be able to get the path length as a vector. We can scalarize it here, just end up with the path length being the speed you're at times the time interval, right? And so in our equation that we had, or our value here for the average acceleration, that delta r vector is going to become essentially the same as that path length, which so it's going to become v delta t. That means we have a v delta t in there. Notice the times are canceling out, and v times v is v squared, and we have an over r, and so boom, that's our formula, v squared over r. Okay, so the direction, we can of course consider this a vector, because it's the direction is kind of abstractly, maybe more so, like it's defined as towards the center. So at any given instant in time, it's not really a vector. Direction is not given sort of directly as east or west kind of thing. It changes all the time. Then, of course, we know net force equals mass times acceleration, and so F, the centripetal force, right, would equal the mass times that centripetal acceleration. Okay, so that is your development. Our summary is, of course, that all objects in uniform circular motion have a centripetal force and a centripetal acceleration, and the centripetal acceleration is v squared over r, and the centripetal force is mass times that acceleration, mv squared over r. Okay, so that is your new equations. So now working with those, we've got a 4 kilogram mass tied to a string. It's in uniform circular motion. The idea right away here is to say, oh, then I know that my net force is the centripetal force, right? And we're given information, and you can just calculate things out. You'd be like, oh, I want to get centripetal acceleration. Well, I know, that's v squared over r. So you just plug the numbers in, and you get your value. I just left it as 2 over 9. You can write it as 4.5. Doesn't matter. Okay. Part B, determine the centripetal force. Well, again, that's just going to be F equals ma, right? So, don't think of FC equals MAC as a new equation. It's just F equals ma, for goodness sakes, right? So just write it, multiply it out. Notice that, keeping that fraction made this kind of easy, right? Because the 2 divides into the 4, giving you a 2. 9 times 2 is 18, right? And then now for our tension in the string. So we've got this horizontal uniform circular motion. Let me just draw a little diagram here for you, sort of a three-dimensional kind of view of horizontal uniform circular motion. We've got a force towards the center, which is our tension, our Ft. And the thing to know, of course, in that scenario is that's the only force towards the center, right? And so we just have that tension force. Okay, so just net force is the addition of all of the forces. In this case, there's just the one. That means our tension force is the 18. Now that's horizontal uniform circular motion. As we talked about before, you can look at vertical uniform circular motion as well. And so now we're going to be able to get forces and get values of tension at the top and bottom and so on based on the speeds. It'll give us the acceleration, which gives us the force, and so on, right? Because we've got rotating systems and so on, it might be tempting to start to think about like the frequency. Like you might be given the period of the rotation, or you might be given the frequency of the circular motion. In which case, these equations can be used. My preference is not to even pretend, like not even look at them ever, because really they're just based on what we know. We know the speed is distance over time, right? And so that's circumference divided by, so there's your v squared, right? Circumference divided by the period. The period is the time to go around and so on. So that thing simplifies to be the centripetal acceleration. And then again, just the reciprocal relationship that frequency is 1 over period and period is 1 over frequency. You see the other one. So, you'll see in my lessons, like my preference is not to use those. I'll give the other option, which I feel is just kind of simpler, less equations to worry about, and the concepts of frequency and period are kind of a little bit more confusing too in the context of questions. So if you can break it down to just getting the uniform circular motion speed, then you can just do v squared over r. Okay, so that's what I'll be showing. I mentioned already, the idea that they really are vectors, but of course it's just towards the center of the circle, right? So we don't usually draw in. You're not really supposed to draw in the vector symbol here because it's a defined direction system rather than a set vector direction at any given time. And that's just a reminder. It's a centripetal force. It's just your net force. And so here we go. We have a mass of 4.45 kilograms on a 1.2 meter cord whirled around in a vertical circle with constant speeds. That's uniform circular motion vertically. And it says, what is the magnitude and direction of the force tension in the cord when it's at the top and when it's at the bottom? So their analysis here, of course, free body diagram. At the top of the circle, it's just the gravity, and then at the bottom of the circle, you've got a tension force and a gravity force, and of course, that FC is not on the free body diagram. FC is the addition of all of those things, right? So in this case, you could say, well, I suppose in this case you could label it because this is 0 here, and so F is it 0 actually? At the top, depends on what we have. No, it's not 0. They just haven't drawn it in, right? So we've got FG and FT. So let's put in an FT as well, right? So let's make a different color for FT. And so at that point, we're like, I don't know how big it is, right? Because we haven't done calculations yet, but it's there. But of course, the addition of this stuff is equal to FC, the centripetal force. And I put a vector bar on out of force of habit. Of course, it's down in this direction in this instant, right? And then, of course, these guys here, Ft plus Fg also equals Fc, right? And again, I could put vectors in because at that instant, at that bottom of the circle, there are defined directions we can work with. All right, so at the top of the circle, well, we know the net force is the centripetal force, right? And we know centripetal force is mv squared over r. So we can just do the calculation. We just have our centripetal force equals the tension force plus the gravity force. That's our F net equals all of the forces added up. And so we solve for that unknown tension force and we get values. Now they have it set up like that, where they've solved for the variables based on variables and so on. I might be tempted, if I was you, to say, okay, my tension that I'm looking for, and then we have the gravity, like at the top of the circle. Are we defining the down as positive? If we are, then we'd have plus whatever the mass is. Mass was 0.45 kilograms, and we'd have the 9.8 because of the down, and then equals the centripetal acceleration, so the 0.45. I'll move this in a second here. The v squared we know is 5, so 5 squared, and over the radius of 1.2. I'm just using the numbers from the work that's there. And again, they're both down, right? These are both down in that down direction. So you can see that's going to lead to opposite signs here. When you subtract across, you're getting this thing subtracted from both sides, of course, like this was right here. Okay, so I just need to shrink that down. And easily here. Oh yeah. Bring that down, and there you go. Anyways, that gives you a value of what looks like it's giving us positive 5. And so there is a tension force down by the cord. So you can tell it's going fast enough that it needs a force from the string in order to stay in uniform circular motion. If this was a negative value, that'd be like a tension force up. You'd be like, ooh, it can't be a string. It would have to be a rigid rod of some sort. At the bottom, similar stuff. I'll just go with their version here. Oh, I need to change my mind. Actually, I don't like that minus being in there like that. But yeah, it would be a minus with the numbers in it, right? So you'd have your mg, and you'd have the 9.8 in as a negative. Okay, so I will go ahead and show that here too. So we've got Ft, and we have plus the gravity force, the 0.45 times that negative 9.8. And the centripetal force at the bottom of the circle is up. So we'd have our 0.45, we'd have our 5 squared, and we'd have our R of 1.2. And just to be really clear here, we've got a minus there and we've got a plus here. This one is um, down. We're going to go at the bottom of the circle, we're going to say up that direction. So this one's down and this one's up. Right? So the centripetal force is up at the bottom of the circle because it has to point towards the middle, which is above it, right? So that math will work out the same, and you'll get a tension force of 14 newtons up. And so notice you get that larger force when you're at the bottom because you're fighting gravity. At the top, you have less of a tension force because gravity's helping you, and so on. Right? Just with numbers and values now instead, right? 1,200 kilogram car, a flat road going on a curve. Radius, we're going to have not flat roads soon. That's banked corners, but not yet. Yeah, radius is 32 meters. And if the coefficient of friction between the tires is 0.50, what's the maximum speed the car can have to make the turn? Okay. So the idea would be that the centripetal force is provided just by that friction force, right? And so we calculate some things, right? We know the centripetal force, and the centripetal force has to be equal to the friction force. So they have, they're just going to solve for V. They asked originally in the question, what's the maximum speed, right? Yeah, that's why they're solving for V. And so you're going to have this, and then of course you're going to use the friction information, right? So friction is mu Fn, and so that mu Fn is going to go in here. You can see we're going to have, regular stuff. They're pointing out the normal force is just normal gravity force, right? You might say acceleration in the y direction is 0, therefore blah blah blah, right? And you're because you don't have any banked corner stuff going on, yeah, they're going to be the same. I don't think they even drew this to be the same. They're just slapping it on there, and then afterwards you can see it's the same kind of thing, right? But there you go. There's your coefficient of friction times the normal force in there. Notice something here. They gave us the mass of the car as 1,200, which always feels nice, right? You can calculate the gravity force if you want in advance and so on. But take a look at that. Mass doesn't matter. It kind of drives me crazy when they give a mass in a question if you don't need it. But I mean, it's the best of both worlds if they do that, and then we also notice that we don't need it, right? Because if the mass isn't given, the textbook author probably knows like students are going to be confused about it. But hey, there you go. There's that mass doesn't matter thing. And yeah, so your speed would be maximum speed would be 13 meters per second, or multiplied by 3.6 to get your kilometers per hour. And mass 4.45 attached to the end of a cord, whirled horizontally on a slippery surface. If the cord can withstand a maximum tension of 30, what's the maximum speed it can get? So very similar stuff here, right? You're going to calculate out what speed leads to that certain tension force. So I think I can just, say, yeah, same stuff. Okay. Ferris wheel, radius of 15 meters, and a period of 30 seconds. Okay, this period of 30 seconds thing kicking in here. Okay, I'm going to show you both versions. So the first thing, of course, know that the addition of those forces, so the force that they're asking for the tension force that these sprockets or these supports are applying, right? So to the mass. And so at the bottom of the circle, you got the force of the structure holding, and you've got the gravity force. And the net force is the centripetal force. Now they went ahead and looked at the formula based on the period of the thing and so on, and the radius and so on. Or of course you could calculate the uniform circular motion speed. Then the simpler equations that are super easy to remember can be used. So if you just fired numbers in to this, you'd have your centripetal force equals your forces added up, your tension and your gravity. And so they have in here solve for that, solve for the unknown FAPP. Which one's that? The tension force, the applied force on the mass. And so they just plug numbers in. They plugged a 60 in by or 30 in by accident instead of a 60. So I'm just fixing that and saying, okay, yeah, we got your 1.2 times 10 to the 3 newtons, right? If we went about this in a more easy to follow method, you just know that your speed is circumference divided by period is the time for one revolution. So you'd have your circumference divided by 60 gives us, that 1.57, and then your centripetal force is this value, right? So the 19.7 is actually in here. Just doesn't look like 19.7 in their calculations because they didn't show it. Yeah, same stuff though. Net force, your tension force plus your gravity. We're at the bottom, so the tension force is up and the gravity is down. The net force is up, so all my signs are in correctly. Let me just emphasize that I looked at that as my direction system, and so I deliberately made that be a positive and this be a negative. And then of course then the tension force or the applied force on the mass from the structure solves out to be whatever it needs to be. Okay? So yeah, that works. No fancy equations needed, really. Just do it. And then at the top, same kind of stuff. At the top, you have this, you could have a tension force down. So the applied force down, they're not really showing very well here. That applied force down, right? Or it could be this way, right? We don't know. And so we just sort of look at the possibility of it, let the math work out to give you the numbers. So same kind of thing. We've got our centripetal force. We can plug the numbers kind of blindly into that crazy equation and get values. If actually in the past I didn't show it both ways, and so I didn't even notice there was a mistake. No one noticed there was a mistake. No one caught it. I go and put this time around the my preferred idea here of the getting the uniform accelerations speed, uniform circular motion speed, sorry, the 19.7 business. The force that ends up being, I should say, the speed was 1.57, I think it was. And I put that in, I calculate things out, and I get a different value. And I'm looking at it, trying to figure out why. I realized that they put in a 30 instead of a 60. So yeah, so we notice that this is up, right? Same deal where I have my direction systems decided at the top. At the top. Oh, sorry, at the top. Yeah, my FC, I thought I had FC in as positive, which would be wrong. It has to be down, right? But I've got my down, and I've got my tension force that I don't know, and yeah. So is that wrong right now? To think of this, my FC should be down. If that's down, I'm going to add that up. Just have to check my work here. I think that I might have a small error. 1 second. All right, all fixed. I'll show you what I looked at here. I went up back to the original, and my tension force, needs to be whatever it ends up being. I've got my gravity down. I've got my centripetal acceleration down. And so when you add to both sides, we end up with exactly what I'm ending up with here, where I add to both sides. I end up with this correct number now, not the one I had by accident there. Adding that number to both sides. So all that happened in my error when I was planning this out was I added those things together instead of subtracting by accident. And I didn't have the negative in here like I should have, right? So directions matter, of course. Yeah, so the angle, add an angle, right? So determine the force applied by the ride at location E. I added in a new one for us here. So it wasn't in the textbook, but it's good to be able to do. So we need to get that angle, right? Well, that angle would be 360 degrees divided into, it looks like 10 equal pieces, right? So we're going to have a 36 degree angle there. And free body diagram for that thing, you're going to have the gravity force on it. You're going to have the tension force that it's applying, presumably because I know it's going slow. It's out that way. And then we have the x component of the gravity force. And then these guys here are going to add up to Fc, right? So I can maybe show with orange here. But these right here and here add to Fc just for emphasis here, which you're going to see in this right here. And yeah, we know our net force is our centripetal force. And so we know that Fc equals this stuff, right? We've got Fc equals those guys. And so the signs here, I think I'm emphasizing, we have the centripetal force. If we define the x direction as that way, then the centripetal force would be in the negative direction. And the gravity x component would also be in the negative direction, wouldn't it? Okay. Add that number to both sides, get your tension force. Notice that it's positive, and so that shows that it's outward, meaning the thing's going slow. It's a Ferris wheel, not a thrill ride kind of thing, right? Where you're held in by the spinning extreme amount of spin or whatever. This guy here is just fill in the blanks from between the centripetal force, mass, centripetal acceleration, radius, velocity, and then period and frequency. If I wouldn't worry about those as much, but I mean that's just a fill in the blank. It's just a bunch of questions in one. So that is that. Thanks for watching as always, and I'll see you next time.